We present end-to-end in-hand 3D reconstruction for partial view object manipulation. Imagine a robot with a single RGBD camera trying to manipulate an object. From any one viewpoint, it only sees part of the object, which isn't enough for reliable grasping or resetting of the pose. We could try to use a powerful 3D reconstruction method like depth anything, but they're usually scene focused and don't give us a fast object-centric model for in-hand use and manipulation. How can we get a good understanding of the object after just one grasp, using the available RGBD data? In this project, we assume the robot can get one decent initial grasp, then use a shortened-hand RGB scan while it moves the object. We adapt depth anything 3 to aggregate those views and output a consistent 3D point cloud of the object that we could reuse for downstream tasks like pose resetting and grasp planning. Adapt depth anything 3 from scenes to objects. Depth anything 3 is a feed-forward neural network that takes a sequence of images and outputs depth maps and camera parameters, enabling scene-level 3D reconstruction. Since it's already trained on 2D to 3D reasoning, we use it as our backbone, and add a few new heads so that instead of reconstructing an entire scene, it predicts the 3D shape of a single object being manipulated. The 3D object reconstruction model uses image features from depth anything backbone that are subsequently passed into our object estimation head, which then predicts the shape that is supervised by chamfer distance.
We gathered training data for the model from YCB objects rotating in the frame of the camera. The YCB objects were either manipulated by the IWA or floating in space. To diversify the training process and encourage zero-shot or few-shot capabilities of shape estimation, we include real-world data from the HOPE v2 dataset, which consists of household and kitchen objects. We collected RGB images, depth images, segmentation masks, and object and camera pose data. Video of data collection involving manipulation of the object using the KUKA IWA is in the top row. Video of the YCB object floating in space in the view of the camera is shown in the bottom row. With manipulation, the IWA first grasps the object from above and holds it in the view of the camera. Then we have the gripper rotate such that the front, back, and sides of the object are captured in the view of the camera. The object is then placed down and re-grasped from the back. The IWA can then hold the object in the view of the camera to obtain unobstructed views of the front and top of the object. The object is then placed down. We use a differential inverse kinematic optimization controller to perform the desired gripper spatial velocity trajectory. The floating object was given a spatial velocity trajectory such that every face of the object was seen by the camera.
Our model's output. On the left top is the input RGB image of the KUKA grasping the mustard bottle, a predicted mask of the object of interest, and the depth estimation of the scene. On the right is the predicted object shape from our new object head, which aligns well with the ground truth head.
Once we have our canonical 3D point cloud model, one useful downstream task that we implemented was what we call pose resetting. If we grab a new object to collect in-hand images and thus know its starting pose and canonical point cloud, when the object's pose is perturbed, we should have the capability to grasp and reset that object's pose back to its original location. Our experimental setup consists of the KUKA IWA arm, a single RGBD camera, and a collection of YCB objects, of which we intend to model and manipulate the yellow mustard bottle. From our model's estimated point cloud of the mustard bottle, we use ICP with several randomly seeded initial poses to align with the partial point cloud produced from the depth output of the RGBD camera. You can see the partial point cloud in red and the aligned model output point cloud in yellow. After we know the object's original pose in the scene, we then perturb the bottle's pose to a different location. As a point of comparison, we first test with the object's ground truth mesh as a controlled baseline. Once aligned with ICP, we generate a set of valid grasps with anti-modality constraints, a height band constraint, gripper collision constraints, and a finger distance constraint. From this set, we pick the grasp that is closest to the mesh centroid in order to heuristically minimize in-hand object slip. We use a pseudo-inverse kinematics controller to place the object back to its original pose. Although, due to simulator friction and the bottle's weight, it rotates within grasp, it is minimal enough to place it upright and close to its original location. We then switch back to the model's output, which is significantly more noisy than the ground truth mesh. While our model predicts a well-masked and visually similar point cloud, the local noise makes it difficult for the grasp planner to find a more stable hold along the main body of the bottle, and settles for a grasp above the upper cap. Being more unstable, this grasp causes the bottle to rotate too much and fall over in the end, but in theory it could successfully complete the full task with more simulator friction. One main limitation of relying on geometric features rather than, for instance, semantic features is that symmetric parts of the object can cause ICP to produce false positive alignments. In the mustard bottle case, occasionally during ICP alignment, it selects a pose that causes it to place the bottle upside down for its final goal pose. For additional improvements, we consider several directions: scaling to more diverse training data, incorporating depth information directly from RGBD cameras, and developing a closed-loop system where multiple partial grasps are fused into a persistent representation for dynamic onboarding. Finally, we would move beyond a simulated tabletop scene and would evaluate and adapt our pipeline in real-world scenes.